Hello, this is John Baugh with another lecture for C++, CIS 2252. And if we look at the syllabus, we'll see where we are. We are on the week of May the 20th, Control Statements Part 1. This covers Chapter 4. So I've uploaded the lecture slides and the supplemental material I've made for you. Which will it kind of summarizes a lot of the stuff that's in the book and also the slides. So we're on schedule here. Some of you are still having a significant amount of problem, it seems, with the DreamSpark related downloads. I have not heard from any of you recently within the last few days, so I'm not sure if these problems have been resolved or if you just threw your hands up and gave up, but I would not recommend doing that because I'm going to be very reasonable and make sure that everyone can get something that they're able to at least compile with. I would recommend, if you can't, absolutely have no way of getting everything sorted out in the DreamSpark world, and you are having problems, then I would say that you should post in the discussion board I added under communications on Desire to Learn. If you are absolutely just unable to get anything to work, I would say for right now, just download the Express version of Visual Studio. It does not, you don't have to download it from DreamSpark. You're probably going to have the same problem if you try to download it from DreamSpark. So just even go to Google and look for Visual Studio 2012 Express, or click on the link that I provided in the news feed and also in the discussion board. You can download Visual Studio 2012 Express. It's I think you might have to register with Microsoft, but I'm not 100% sure. The Express version is just fine. That's actually what the other instructor who's teaching C++ is having his students do, because he said he wasn't using DreamSpark this time. And he said he did not indicate that any of his students had any difficulties. So, excuse me. Today, we're going to go over Chapter 4. We'll start with Control Statements, Part 1. There are a lot of slides, but I'll be breezing through several of them. Some of them I'll focus on, and some of them I'll just breeze through. And I have a little bit of a cold today, so I might be clearing my throat a lot. So Chapter 4, Control Statements. I've got Visual Studio launched already. The objectives are basic problem-solving techniques and to develop algorithms through the process of top-down stepwise refinement, to use the if and if-else selection statements to choose among alternative actions, to use the while repetition statement to execute statements in a program repeatedly, counter-controlled repetition versus Sentinel-controlled repetition. These are two different types, and to use the increment, decrement, and assignment operators. So getting started with the introduction. Before writing a program to solve a problem, we have to have a thorough understanding of the problem and a carefully planned approach to solving it. When writing a program, we must also understand the types of building blocks that are available and employ proven program construction techniques. In this chapter and in the next chapter, since the topic of control statements are quite large actually, we'll learn about logical operators, and we'll discuss these issues as we present the theory and principles of structured programming. So we're going to learn about, in the next chapter, we'll learn more about the remaining control statements that we don't cover in this chapter, and also logical operators as well. So again, as a computer scientist, you have to look at your ultimate goal as not just learning the syntax of a programming language. Although that is important, you have to think of yourself as a problem solver. So you want to make sure that you have a thorough understanding of the problem, and then you plan out an approach to solve it. Okay? So any solvable computing problems, there are problems that are unsolvable. You will learn about that if you go into a higher level a university data structures and algorithm analysis course of some sort. You'll learn that some problems are actually unsolvable by a computer. A lot of them involve paradoxes and things like that that just can't work. Any solvable computing problem can be solved by the execution a series of actions in a specific order. An algorithm is a procedure for solving the problem in the terms of the actions to execute and the order in which the actions execute. So that's what an algorithm is. The algorithm is basically the solution, not just an answer, but a solution, how to do it, how to solve the problem. So it's a solution to the problem. Specifying the order in which statements, also called actions, execute in a computer program is called the program control. This chapter investigates program control using C++'s control statements. This is a huge topic within computer programming, and one of the fundamental things you have to learn in the vast majority of programming languages in order to be successful. Pseudocode, section 4.3 covers pseudocode. Pseudocode, or what we call fake code, is an artificial and informal language that helps you develop algorithms. It's usually similar to everyday English. It's convenient and user-friendly, helps you think out a program before you attempt to write it. Carefully prepared pseudocode can easily be converted to a corresponding C++ program. Normally describes only executable statements, so you typically don't describe the declarations of data. For example, the figure in the next slide, this 4.1, corresponds to some pseudocode. So for example, prompt the user to enter the first integer, input the first integer, prompt the user to enter the second, input the second, add the first integer and second integer, store result, display result. Okay, so that would be pseudocode. It's in English, essentially. There are different forms of pseudocode, but this is one form. Now, the major topic of this this chapter are some of the control structures. So what you've learned so far, normally these statements in a program execute one right after the other. Like, for example, we could have cout, hello world, cout this, cout that, get data. For example, this is called sequential execution or linear execution because it happens in sequence. Various C++ statements enable you to specify that the next statement to execute may be other than the next one in sequence. This is called a transfer of control. Okay, this is where control structures come in. So all programs can be written in terms of only three control structures. These are categories. You have sequence structure, which we've been dealing with from day one. Then there are two that we're going to learn about today, at least a couple from one and one from the other, and then we'll learn the rest next week. You have the selection control structure and repetition, also known as iterative control structure. So these are the two we're going to focus on this week, selection and repetition. When we introduce C++'s implementation of control structures, we'll refer to them in the terminology of the C++ standard document as control statements. So unless directed otherwise, the computer executes C++ statements one right after the other in which they're written. This is called the sequential control, okay, so in sequence. There's also a language called UML. It's for drawing models, essentially, and it allows you to visualize how a program works. So the next figure that we'll look at involves an activity diagram. C++ allows you to have as many actions as we want in the sequence structure. Anywhere a single action may be placed, we may place several actions in sequence. So if I look at the next, the UML activity diagram here, the black dot at the top indicates where the program starts, and the black dot with a circle around it indicates the end of the program. This is sequential structure right here. Okay, sequential or linear structure. For example, add grade to total, and then add 1 to counter. So Notice that the actual actions here are like kind of like rounded rectangles. And then these things off to the side, these are actually just notes. They're comments. They're not just like in an actual programming language. These are considered not really executable. They're just describing what's happening. Okay. So an activity diagram models the workflow, also called the activity, of a portion of a software system. Such workflows may include a portion of an algorithm, such as the sequence structure that we saw in figure 4.2. So this could be a portion of an algorithm. It may not be the whole thing. And remember, an algorithm, essentially, it's a finite ordered set of sequence to solve, or set of statements to solve a problem, and it has to be well ordered, and it has to be terminating, meaning that, or finite, meaning that it can't go on forever. Okay, and the order of the instructions matters. Okay, if you consider an algorithm for baking a cake, obviously putting the pan into the oven first without any cake batter or any of the ingredients, then taking it out hot and throwing ingredients in and then setting it before your guests is probably not the right order. So the order does matter. Activity diagrams are composed of special purpose symbols, such as the action state symbols, the rectangle with its left and right sides replaced with arcs curving outward. This is the rounded rectangle I talked about. These are the action state symbols. Diamonds and small circles, these will represent, the diamonds represent a change in flow of control, so we'll see those later. And small circles, these symbols are connected by transition arrows, which represent the flow of the activity. So again, the activity is made up of sub-actions, okay? The actions that we saw earlier, for example, like add graded total is one action, add one to counter is another action. And they're connected by the transition arrows. Activity diagrams help you develop and represent algorithms, but many programmers prefer pseudocode. Some people use both. Some people will draw out the diagram and then write out the pseudocode after they've got a basic idea about what they're supposed to be doing. Activity diagrams clearly show how control structures operate. Action states represent actions to perform. Each contain an action expression that specifies a particular action to perform. So, the arrows in the activity diagram are called transition arrows because they represent transitions which indicate the order in which actions represented by this action states occur. Solid circle at the top is the initial state or the starting state, and then the solid circle at the bottom with the additional hollow circle around it is the final state or the ending state. The rectangles with the upper right corners folded are just called notes in UML, so they're basically just comments. And then the dotted line connects a note to an element that the note describes. Okay, so now getting into the actual C++ world. The C++ provides three types of selection statements. Remember that we have three categories of control structures, and you can make essentially any program from those. These are the sequential control, which we've used from day one, selection control statements, which allow us to pick between or among different options, and then repetition control statements, which allow us to repeat a block of code until a certain condition is met. So right now, if we look at the selection statements, there are three types of selection statements. We'll discuss these in this chapter and chapter 5. The if selection statement, the if single selection statement, selects an action if a condition, which is called the predicate, is true or skips the action if the condition is false. Okay, so it either does it or does not do it based on a condition. If else selection statement performs an action if the condition is true, or performs another action, a completely different action, possibly, if the condition is false. And then in chapter 5 we'll learn about the switch selection statement, which performs one of many different actions depending on the value of an integer expression. So let's start with the if statement. The if selection statement is a single selection statement because it selects or ignores a single action, or as we'll see, a single group of actions, If-else statement is called a double selection statement because it selects between two different actions or a group of actions. And then the switch selection statement is called a multiple selection statement because it selects among many different actions or groups of actions. So C++ provides three types of repetition statements, also called looping statements or loops. So again, we've got sequential, selection, which we just talked about, if, else, and switch. And then there are three types of repetition statements called looping statements or loops for performing statements repeatedly while a condition called the loop continuation condition remains true. These are the while, do while, and for statements. While and for perform the action or group of actions in their bodies 0 or more times, and do while performs the action or group of action in its body at least once. Okay, we'll see why that's the case later on. Each of the words if, else, switch, while, do, and for are C++ keywords or reserved words. These words are reserved by the C++ programming language to implement various features such as C++'s control statements. These keywords cannot be used as identifiers. For example, you cannot name a variable if. Okay, you could put if2 or if3 or if4 or ife, ifa, whatever you want in that case, but you cannot use the actual word if. That is a keyword in C++. So this is a complete list of C++ keywords. Some of them are inherited from the C programming language, from which C++ gets its name and much of its program structure, and some of them are C++ only keywords. These are keywords that are not keywords in C. Here are some more. You can look over those at your own leisure. So control structures. Each program combines as many of each of these control statements as appropriate for the algorithm the program implements. So an algorithm, the solution to a program or a problem, can be independent of a particular implementation or particular programming language. So we can model each control statement as an activity diagram with initial and final states representing that control statement's entry and exit points, respectively. Single entry, single exit control statements. These are control statements that are attached to one another by connecting the exit point of one to the entry point of the next. This is called control statement stacking. Only one other way to connect the control statements called control statement nesting, in which one control statement is actually contained inside another. Okay, this will make a lot more sense once we see examples, so if you're feeling a little bit overwhelmed, don't worry about it. Okay, so the if selection statement. Now we're going to focus in on the if selection statement itself. Programs use selection statements to choose among alternative courses of action. Okay, so again, the transfer of control that we're going to be dealing with. The transfer of control involves not going in sequence in every circumstance. Sometimes you're going to go to a programming statement that is not listed in sequence. So the following pseudocode determines whether student's grade is greater than or equal to 60 is true or false. So here's our if selection statement in pseudocode. So basically in English it says if student's grade is greater than or equal to 60, just print passed. Okay. If true, passed is printed and the next pseudocode statement in order is performed. Remember that pseudocode is not a real programming language. If false, the print statement is ignored and the next pseudocode statement in order is performed. So if this is true, it will print passed. If this statement students greater than or equal to 60, let's say the student's grade is 58 or 57 or 40, anything below 60, it will actually skip this statement right here because that is attached to this if statement right here. So the indentation of the second line is optional, but it's recommended because it emphasizes the inherent structure of structured programs. For example, this is indented because this belongs to this conditional selection statement at the top. So the preceding pseudocode if statement can be written in C++ like this. So if grade greater than or equal to 60, you print out passed. Okay, so I'm going to actually create a program here. I'm going to create a new project. You can go to File, New Project, or just click New Project at the Start menu. Making sure I'm in the directory that I'm happy with and that I have console application selected. I'm going to call this Lecture 3 Control Statements Part 1. Hit OK, then hit Application Settings, make it an empty project, and click Finish. When you create the empty solution, again, you have a program that contains folders in it, project that contains folders in it. I'm going to create in the source files a new item. Make sure it's a C++ CPP file. We're not really dealing with classes extensively right now, so I'm just going to make one CPP file, main.cpp. Alright, and we'll put this standard skeleton program that we have put in previous examples. I'm going to make an integer here, integer grade. Alright, and then we're going to say, we could initialize the grade just to make sure it has a value of some sort. I'm going to print out enter a grade. Okay, and then I get the grade in from the keyboard, and then if the grade is greater than or equal to 60, now I could put it on one line and not use the curly braces there, but for this example I'm going to put the curly braces around it. I actually prefer curly braces even if it's one statement in here, because if you don't put the curly braces, then the if statement only applies to the very next statement. If I come along, even if I indent it and say cout something else, you might ask yourself, well, which one actually is affected by the if statement? The if statement only affects this one right here. This one will always execute. This, even though we indented it, it has nothing to do with the if statement. So to ensure that everything that you want to be affected by the if statement is included, you want to put curly braces around it. So I do it even when there's only one statement. So we could build and run this. Alright, wait until it builds, then run it. And it says enter a grade. I'm going to enter a 62, so it'll say passed. And then if I run it again, if I say a 49, it doesn't do anything, right? It just exits. Press any key to continue. So this is the power of the if statement. It either does or does not do something based on this condition called the predicate. Okay. So in a UML diagram, which you may see quite frequently in this and other books, the diamond or the decision symbol indicates that a decision is to be made. The workflow will continue along a path determined by the symbol's associated guard conditions, which can be true or false. Each transition arrow emerging from a decision symbol has a guard condition in square brackets above or next to the transition arrow. If the guard condition is true, the workflow enters the action state to which the transition arrow points. Okay, well, this is what this looks like. Here are the guard conditions inside of the brackets. UML diagram. Again, you start here with the dark black circle, the initial state, and then the final state or ending state has the black circle with the hollow circle around it. So we know that this will end eventually, but right here when we get to a diamond, that means a decision's made. So we're not going just in sequence automatically. Now if the grade's less than 60, it'll go from here to there to there, but if this grade is greater than or equal to 60, it will actually divert or transfer control over here, print passed, and then it will go to the final condition down here. So decision can be based on any expression. If the expression evaluates to 0, it's treated as false. If the expression evaluates to non-zero, it's treated as true. But to make things a little bit easier on the eyes and look more organized, C++ provides the data type bool for variables that can hold only the values true and false. Each of these is a C++ keyword. Okay? So for compatibility with earlier versions of C, which used integers for Boolean values, the bool value true also can be represented by a non-zero value. Compilers typically use 1. And then the bool value false is represented as the value 0. Now notice this is something that involves C++. Other languages, the true is not always compatible with 1 and the false is not always compatible with 0. Okay, they're built-in data types and in other languages, or built-in constants in other languages that are not compatible with just 0 and 1. Okay, so always keep that in mind if you're dealing with another language. You can't say, if something is equal to 0 or equal to 1 in all languages. In C++, for backwards compatibility with C, they did make it this way. Okay, so we dealt with the if statement. It either does something or does not based on the condition or the predicate. The if-else double selection statement. If-else double selection statement specifies an action to perform when the condition is true and a different action to perform when the condition is false. So for example, maybe the pseudocode says if the student's grade is greater than or equal to 60, we print pass, otherwise we print failed. So let's go back to our code here and modify it so it's now going to be an if-else double selection statement. I'll put failed here. All right, so we have passed. Before, what we had is we just had this, so it either printed out passed or it printed out nothing. Okay, now you could have put other statements below it. That's no big deal. But if we want it to choose between the two statements to print out, then we have to put an else section here. Okay, so this means if it satisfies this condition right here, grade greater than or equal to 60, do this. If the predicate is not satisfied, then you do this. So let's see what happens now. If I build it, I run it, I'll enter the grade 62. It'll print pass just as before. But before, if I printed a value lower than 60, such as 40, before it just exited the program. It didn't do anything. But if I do it now, it'll say failed, because I specified it should do something else. This is the something else it should do. Failed. Okay. In either case, after printing occurs, the next pseudocode statement in sequence is performed. So they give you an example here. Again, their preference, at least up to this point, is that they don't put the curly braces around the statements. This would work in this case totally fine because there's only one statement to print for each of these conditions. So this is an if-else program control in UML diagram. You have the diagram, or the diamond, which indicates that there's a decision to be made. So it's either greater than or equal to 60, the grade, or it's less than 60. So if it's greater than or equal to 60, print passed. If it's less than 60, print failed. And then ultimately they both arrive at the final condition, final state. Okay, so the conditional operator is an operator that's allowed. It's closely related to if-else statement. It's C++'s only ternary operator, which means it takes 3 operands. So its syntax is a little bit squirrely. A lot of people don't like it and don't use it for that reason, but sometimes it can be useful. It's very compact, so it's easily writable if you know what you're doing. It's just a little bit harder to read, especially if someone looks at it and has no idea what's going on. And it's not available in a lot of languages, so some people might get kind of confused and think, well, what is that? I don't know what that means. So the operands, together with the conditional operator, form a conditional expression. The first operand is the condition, so that goes before the question mark. The second operand goes between the question mark and the colon. That's the value for the entire conditional expression if the condition is true. And then the third operand, which goes after the colon, is the third, or is the value of the entire conditional expression is false. So you've got condition, value of true, value of false. So you can nest if-else double selection statements like this. So I can have one inside the other, essentially is what you're doing. So it would look like this if it was actual code. For example, if the student grade greater than or equal to 90, print an A. else, and then you can have this if else in there, this if else inside of that one, this if else inside of that one. This is typically written like this, though. Okay, most people don't even think of it as chaining them or nesting them when they write it this way, but this is much more common syntax, as you'll put the else and then the if for the next one on the same line. So we tend to think of it as when we're programming, a lot of people tend to think of it as a separate control structure, even though it's not. Okay. A nested if-else statement can perform much faster than a series of single selection if-else statements because of the possibility of an early exit. So what does that mean? Well, I could put each of these as a separate if statement, right? And it would satisfy certain conditions, but the problem, there would be multiple problems here. If the grade is greater than 90, then it's also greater than 80 and greater than 70, greater than 60. So it's going to print out the A, the B, the C, the D, and the F, or not the F. It won't print out the F. That's the only thing it won't print out. Because it won't satisfy this condition. This is if we had each if statement separate. But if we chain them like this, as soon as it finds a condition that is satisfied, such as this one, let's say they get an A. If this is satisfied, they get a 90, 91, whatever, it'll print out the A, and then it'll break out around all the rest of these and then start performing or executing the code under it. If these were all if statements, it would test each one independently. So that's one reason why there's an efficiency and also a meaning difference. So the C++ compiler always associates an else with the immediately preceding if statement, unless told to do otherwise by the curly braces. This is another reason that I typically use the curly braces all the time, because if you look at some of this code right here, you might think, because of indentation, that this one and this one are connected. The if x greater than 5 and the else x is less than or equal to 5. But actually, since it only applies to the immediately preceding if statement, this else is actually connected to this if. Okay, so even though because the indentation really has no effect on it. All right. So the compiler interprets it as this. So to prevent that from happening, you could do this. You could put the curly braces around this and force the else to be connected to this if statement. All right. Okay. So we call basically a set of statements, one or more statements inside a curly braces, the block of code. Alrighty, so just as a block can be placed anywhere in a single statement can be placed, it's also possible to have no statement at all. This is called a null statement or an empty statement. Okay, so you just put a semicolon at that point. I'm going to take a brief break, and I suggest you do the same. So I'm going to pause this here. Obviously, it'll not look to you like I'm pausing, but I'm going to pause this, take a brief break, and then we'll get to while repetition statements. Okay, so now we're going to work on the repetition statement. So this is a repetition statement, also called a looping statement, where loop always allows you to specify that a program should repeat an action while some condition remains true. Okay, so here would be the pseudocode. While there are more items on my shopping list, purchase next item and cross it off the list. So you use these types of things in your daily life, you just haven't written them in code yet, probably. So there are more items on my shopping list is either true or false. If it's true, purchase next item and cross off the list is performed. So you perform this repeatedly while the condition remains true. When the condition becomes false, you're done with this code. So consider a program statement designed to find the first power of 3 larger than 100. Suppose integer variable product has been initialized to 3, such as this. When the following while repetition statement finishes, executing product will contain the result. So it's going to keep multiplying by 3 until it gets to the point where this condition is no longer true. So remember, it tests the condition first because it's what we call a pre-test loop, and then it'll say product equals 3 times product. So that'll go to 9, 27, etc., etc., etc. And then it will print out the largest. If we want to do a print statement under here, it would print out product, which would then contain the value the product that has been multiplied by 3, the power of 3, first power of 3 that's larger than 100. So, this is an error to avoid here. There's a logic error called an infinite loop, in which the repetition statement never terminates. This occurs if you do not provide an action in a while statement's body that eventually causes the condition in the while to become false normally. This can make a program appear like it's hanging or freezing if the loop does not contain the statement that interacts with the user. So, while repetition statements in UML, we use a merge symbol, and the UML represents both the merge symbol and the decision symbol as diamonds. The merge symbol joins the transitions from an initial state from an action state so that they both flow into the decision. The decision and merge symbols can be distinguished by the number of incoming and outgoing transitions. So a decision symbol has one transition arrow pointing to the diamond and 2 or more transition arrows pointing out. Each transition arrow has a guard condition next to it. A merge symbol, okay, these are again both diamonds, so how to distinguish between them. The merge symbol has 2 or more transition arrows pointing to the diamond and only one transition arrow pointing from the diamond to indicate multiple activity flows merging to a continue activity, or merging to continue the activity. Unlike the decision symbol, the merge symbol does not have a counterpart in C++ code. We just represent these in loops. So right here we have a merge. All right, this is basically where the top of the code, say in a while loop or what have you. We have the test, and then triple the product values and action. Go back to the top, do the test, and then test the condition, true or false. If it's true, you go this way again and triple the product. Keep going until this condition right here is no longer true, and then this one would be. So then you continue along your way. So this is where the actual merge occurs. This is the decision that's performed. So how do we formulate algorithms with counter-controlled repetition? So consider the following problem statement. A class of 10 students took a quiz. Okay, so you've got 10 students. They have grades 0 to 100 for this quiz, and these grades are available to you. You want to calculate and display the total of the grades and the class average. So the class average is equal to the sum of the grades divided by the number of students, right? So a simple math problem. If I were to tell you to do it, I give you the 10 students and tell you to do it in a math problem in one of your math courses. You could probably do this pretty easily. You'd add up the 10 grades, divide by the number of students, so that would be 10 in this case. We can write an algorithm to have the computer program solve it for us. So the algorithm for solving this problem on a computer must input each of the grades. Okay. Then we also have to calculate the average and then print the result. Okay. So for this one, we're going to use what's called counter-controlled repetition to input the grades one at a time. This technique uses a variable called a counter to control the number of times a group of statements will execute, also known as the number of iterations of the loop. So that's why repetition control statements are also called iterative control statements. Often this count-controlled repetition called the definite repetition because of the number of repetitions is known before the loop begins executing. Okay, so here would be some pseudocode. So pseudocode for solving the class average problem. You set the total to 0 and set the grade counter to 1. While grade counter is less than or equal to 10, you prompt the user to enter the next grade, input the next grade, add the grade to the total, and then add 1 to the grade counter. Well, why do we need the counter to increment? If you don't do anything to the counter, this loop condition will never be satisfied, because the condition is, it will never not be satisfied. It will always be true, because while the grade counter is less than or equal to 10, it would stay at 0 if we did not modify the grade counter and have it increment, have it go up. Okay, so eventually we want it to be equal to 10 or greater. So, well, in this case, it would be equal to 10. It would still go. So when it got to 11, this would no longer be true, and it would break out. So we have to make it eventually break out. So set the class average to the total divided by 10. Set the total number of grades for all students in the class, and then print the class average. Okay, so we'll see the code in just a moment. A total, okay, is also called an accumulator. It's a variable used to accumulate the sum of the several values. The counter is the variable used to count. In this case, the grade counter indicates which of the 10 grades is about to be entered by the user. Variables that are used to store totals are normally initialized to 0 before being used in a program. Otherwise, the sum would include the previous value stored in the total's memory location. So when you declare a variable and reserve it, there could be garbage sitting in the memory that total is referring to. The problem, or to solve that problem, all we have to do is initialize its value to 0. So whatever was in there before and freed up by the operating system for our use or what have you, we would just set it to 0, and it would change the value there. Now they use a class version here. We wouldn't necessarily have to use a class in order to get this to work. But they've got their gradebook class that they deal with. They actually deal with this for several chapters. I'm not a particularly big fan of the class, but it's because they use it in a lot of different books. They seem to reuse a lot of the stuff, which I guess is good. But this is the constructor. Then you have the set course name, get course name, display message, and then determine class average. So this is the one that really I think we're concerned with. So here's the definition. You set the course name to name in the constructor. The set course name determines if the name that you pass in is less than 25, size 25 in its length. Then you set the course name to name. Otherwise, you set the course name, and then they're using the string function substring. They basically truncate anything greater than the 25 characters. So 0, they start at position 0 and go 25 characters. This limits the course name. So then it will print out an error. It'll say it'll exceed the length, so limiting course name to first 25 characters. So that's kind of a solid way to make sure that the code works, and you still have your limit put in place. The function to retrieve the course name is very easy. Just return the course name. We'll get to the code that actually is important in just a second here. Display message. This will say welcome to the gradebook 4, and then get the course name. Again, notice that we're reusing some of the methods we already have here. This is where the new stuff goes. So you don't really have to make this unsigned, but making it unsigned means it'll only have positive values in it. So they're using this and calling this grade counter. They're saying while the grade counter initialized at 1 is less than or equal to 10, you could also initialize it to 0 and go up explicitly to less than 10 instead of less than or equal to, and that'll still count 10 grades because the first grade will be at location 0. They'll say enter the grade. They initialize a grade down here to 0, input the grade, set total equal to total plus grade, so this is accumulating the total, and then you'll notice that they're incrementing the counter here. They're saying grade counter equals grade counter plus 1. Alright, then when this loop is over, okay, so when it's accumulated all 10 grades, they go here, and then they calculate the average. So the averaging calculations performed in member function determine class average using local variables, so they don't have to preserve any of the information about student grade in the class's data members. So continuing here, you'll normally initialize counter variables to 0 or 1 depending on how they are used in an algorithm. An uninitialized variable contains what we call a garbage value, or an undefined value. This is a value that was last stored in memory at that location. It's not necessarily by your programs. It could have been an integer or some sort of value put there by a previous program that was using that memory. Okay, so they give you some helpful tips. I'll let you look over those at your own leisure. My gradebook determining class average, or determine class average. This is how you actually call it in main. Declare the gradebook, display the message, welcome to this class, and then you're saying determine class average. So then they print out the grades, or not print out the grades, but you enter the grades for each of them, and then it'll say the total of the grades is 846, class average is 84. So the averaging calculation performed as in response to the function call produces an integer result. You might look at this and say, well, technically 846, since that's the total, divided by 10 should be 84.6. Well, what happened to the 0.6? If you'll recall, in the code, we actually divided by 10 and stored the value in an integer. So integers cannot hold fractional values. So basically what happened is that that extra data was truncated or removed. Okay, so we call that truncated or discarded. So a note about arithmetic overflow. Total equals total plus grade. Added each grade entered by the user to the total. Even this simple statement has a potential problem. Adding the integers could result in a value that's too large to be stored in an integer. This would be called arithmetic overflow. It causes an undefined behavior. So you could look even on Wikipedia and look at integer overflow and the security ramifications of that. However, since we only have 10 items and the grades are limited 0 to 100, we are definitely within range and we're good. Especially for learning purposes. So, the addition program had the same issue in line 19, which calculated the sum of two integers entered by the user. The maximum and minimum value that can be stored in an int variable are represented by constants, int max and int min. These are actually available in the header C limits. Okay, so that's provided for you. It's actually provided in C++. It is not a value, a value that you determine. Okay, so there are similar constants for other integral types and for the floating point values, so C limits, C floats. Okay, so anytime a program receives input from the user, various problems might occur. So for example, you have cin, use the stream extraction operator to grade, so that means it'll take it from the keyboard, store it in grade. We assume that the user will enter an integer grade from 0 to 100. However, the person entering the grade could enter an integer less than 0 or an integer greater than 100, which are integers outside the range that we're specifying, or they could even enter an integer outside the range of values that can be stored in an int. So a number containing the decimal point or a value containing letters or special symbols that's not even an integer. So to ensure the user's input is valid, we would use tests to make our program more robust, or in what they're referring to as industrial strength programs. These are programs that you would release and actually use in the industry. So let's generalize the class average problem. So develop a class average program that processes grades for an arbitrary number of students each time it's run. So the program must process an arbitrary number of grades. We can use a special value called a Sentinel value, also called a signal value, dummy value, or flag, to indicate end of data entry. Sentinel-controlled repetition is called indefinite repetition. This is to distinguish it from our count-controlled or counter-controlled repetition that we saw before, where we knew there would be 10 grades before. Sentinel-controlled means we're not sure how many we're going to have, so the sentinel value must not be an acceptable input value, and the sentinel value, if encountered, it says, hey, we're done entering data. Okay, as a kind of an aside, as a software engineering programming technique, we approach the class average problem with what we call a top-down stepwise refinement technique. This is a technique that's helpful to develop well-structured programs. We begin with a pseudocode representation at the top, so it's a single statement that conveys all the overall function of the program. Determine the class average for the quiz for an arbitrary number of students. So the top is, in effect, a complete representation. Rarely conveys sufficient detail, so it's very general usually, and it just says what does the overall algorithm solve, what are we trying to do. Then you refine it. So divide the top into a series of smaller tasks and list these in order. This is the first refinement. Initialize variables, input sum and count the quiz grades, calculate and print the total of all the student grades in the class average. This refinement uses only the sequence structure. These steps execute in order. Okay, so that's another refinement. In the second refinement, we commit to specific variables. So pseudocode statement input sum and count the quiz grades requires a repetition statement that successively inputs each grade. We don't know in advance how many grades there are, so we'll use what's called Sentinel-controlled repetition, which we talked about briefly before. So the user enters legitimate grades one at a time. After entering the last legitimate grade, the user enters the sentinel value. So the program tests for the sentinel value after each grade is input and terminates the loop when the user enters the sentinel value. So the sentinel is like a special value. Okay, so prompt the user to enter the first grade, input the first grade, possibly the sentinel, and then while the user has not entered the sentinel, keep adding the grades to the running total. Okay. Oh, also note that dividing by 0 causes, even though they spelled causes wrong, that's lovely, dividing by 0 causes undefined behavior and normally causes a fatal runtime error. That means your program crashes. So unless you're Chuck Norris, you cannot divide by 0. All right, so you keep refining it until you come down with something that can be interpreted as C++ code, actually implemented in C++ code. So what about our average calculation from before? Let's solve one problem at a time here. An averaging calculation is likely to produce a number with a decimal point. So a real number, for example, or a floating point number, 7.33, 0.00975, etc. Type int cannot represent such a number. So C++ provides several data types for storing floating point numbers in memory, including the float and double. Compared to float variables, double variables can typically store numbers with larger magnitude and finer detail. A cast operator, which we will see, can be used to force the averaging calculation to perform the floating point numeric result, or provide the floating point numeric result. So there's also a library called IOManamp, which we will look at. This is for parameterized stream manipulators. We'll see those in a second. If we go down here and look at our class averaging example, we'll say instead of enter 10 grades, we're going to say enter grade or -1 to quit. Well, you might think, well, what the heck's the -1? The -1 is our sentinel value. So we still need to count them in this case. This is not to terminate the loop, but that's because we need it for the average function. If we didn't need to count them, then we wouldn't need to use a counter variable at all. But we're initializing the grade to 0. Notice it is local to here, not inside of the loop. Then we input the grade. If they input a -1, that would be the sentinel value. You might think, well, why is that the sentinel value? Why not just use a 0 or a 5 or a 10? Well, what was the specification for a sentinel value? It has to be a value that is not a valid value. So a 0, a 5, or a 10 would be a valid value for a grade. So -1 is not a valid grade value, so we're going to use that as the Sentinel value. Then, in the while loop, we'd say while grade not equal to -1, this is the Sentinel, we keep adding grades, or adding grades to the total. When you're done, then at the end, we do a test here. Now we could leave this test out, but then you might think, well, why would we do that, or why would we perform this test even? The reason we're performing this test and we say grade counter not equal to 0 is because if the number of items, the number of grades is 0, later on we're doing what? We're dividing by 0. That would be bad. So we're saying if the grade counter is not equal to 0, we do all this calculation. Now, you might think, what the heck is this thing? Well, the static cast, a cast, we're performing on the total. You could also do a C-type cast, which is just put double in parentheses around the total. You have to convert this, cast it, into a double before you perform the operation here, because if you don't, you're going to have an integer and an integer, total and grade counter, and that'll still truncate it, and then it'll store the truncated value as a double. So you'll have the same problem as before. So you have to solve that by casting one of these as a double. Once one of them, at least one of them, is casted as a double or started as a double, you could make total a double. You could declare it as a double earlier if you wanted to. But once you have that as a double, you can perform the division, and it will perform floating point division, not integer division, so you won't lose data. Later on, they have set precision and fixed. That will affect how the output is done. So I'm not going to spend a ton of time on how that works, but basically the set precision fixed to 2 allows you to put the average, to limit the average to 2 decimal places. Okay, I'll let you look in the book as to the specifications for the IO manip. So 85.67, and you also have the totals in integers. Okay, notice the block in the while loop. Without the braces, the last 3 statements in the body of the loop would fall outside the loop, causing the computer to interpret the code incorrectly. So you have to put code inside curly braces if you have more than one line. I recommend doing it regardless. Same thing for selection control structures as well. Okay, we can skip that. Okay, truncated. Okay, the cast operator. To perform a floating point calculation with integers, create temporary floating point variables. You use this with the static cast operator. So static cast double on total creates a temporary floating point copy of its operand. Now the operand is this, and even though total is an integer, it creates a temporary floating point copy of its operand and returns it. This is called explicit conversion. Okay, the value stored in total is still an integer. You're not actually modifying, like changing the data type dynamically or something. The total is still an integer. This just returns and creates and returns a floating point copy. The calculation now consists of a floating point value divided by an integer grade counter. The compiler knows how to evaluate only expressions in which the operands of types are identical. Compilers perform what's called promotion, also called implicit conversion, on selected operands. In the expression containing the values of type int and double, C++ will promote an int operand to double. So that's why we were able to perform a floating point division, because we had created the temporary floating point here before dividing it by the grade counter. It will promote grade counter to double temporarily when it does the compilation. Okay, set precision indicates that the double value should be printed with 2 digits of precision to the right of the decimal point. IndL is a non-parameterized stream manipulator we've used before. It does not require IO manip. If the precision is not specified, floating point values are normally output with 6 digits of precision. So that's why we set precision to 2. The string manipulator fixed indicates that floating point values should be output in a fixed point format as opposed to scientific notation. Fixed point formatting is used to force a floating point number to display a specific number of digits rather than try to print out scientific notation, for example. All right. When the string manipulator's fixed and set precision are used in a program, the printed value is rounded to the number of decimal positions indicated by the set precision. So if I rounded it to 2, or if I specified set precision of 2, it will actually do rounding. It doesn't truncate. It does rounding when you do set precision. It's also possible to force a decimal point to show, even if there is no decimal. Let's say that you have a value 88.00 as your double. We can still force it. Instead of printing out 88, we can say show point, and it will force it to show the decimal point. Okay, let's go through here. Nested control statements. Oh, we pretty much covered that. For fundamental type variables, list initialization syntax also prevents the so-called narrowing conversions that could cause data loss. So for example, if you could write int x equals 12.7. Well, what's the problem here? Well, 12.7 is a double. If you try to store it in an int, it will cut off the 0.7, right? So double value is converted to an int by truncating the floating point, 0.7, which results in loss of data. So this is list initialization syntax. This is if we created an employee class, we could actually put list initialization syntax with the different types specified here. If you do it here, the list initialization syntax prevents narrowing conversions. So if you have something that's expecting a double here, or an integer here, and you specify a double, you're going to get an error. So narrowing conversions are completely unallowed in some languages. Like Java will actually flag a compiler error if you try to perform a narrowing convention, or conversion. If you are losing data, it's called a narrowing conversion. If you're going, let's say this is a double. If I say double x equals 12, and I just specify this as an integer, it will convert it to 12.0 with no problem. Well, you might ask, why is that the case? Isn't that a narrowing conversion? No, it's not. If you have the data it's being stored in as larger or more specific than the actual value you're specifying, then that's called a widening conversion. So widening conversions are okay. You're not going to lose any data. Okay, so you could try this, but you're going to end up with a problem if you use the list initialization syntax. It will give you an error for doing this, but very few people actually use this syntax to initialize a standard typical variable if you try to use list initialization syntax, but this will force the compiler to generate an error. Many compilers just generate a warning, though. Okay, so it may give you a warning, say you could lose data, blah blah blah, but it'll give an error if you use list initialization syntax. There are several assignment operators. These are important for abbreviating assignment expressions. For example, we have plus equals. This operator adds the value of the expression on the right of the operator to the value of the variable on the left, and then stores it back into the left. So it's kind of a shortcut. For example, C plus equals 3 is the same as if I said C equals C plus 3. So it's shortcut syntax. It's used extensively, so this is something you want to become familiar with. These are more examples: plus equals, minus equals. These are the compound arithmetic assignment operators. So you have the addition, compound addition assignment operator, compound subtraction assignment operator. This gives you sample expressions, an explanation of what it actually would expand to if you were to write it out long ways, and then what does it do. C++ also provides two unary operators for adding one or subtracting one from the value of a numeric variable. These operations are so common, adding one or subtracting one to a variable, that they've actually created an operator for them in C++. Many high-level languages, Java, for example, C#, have the increment and decrement operators. So plus plus and minus minus. They're summarized in here. Whether they're before or after, what they're doing is they're incrementing the values by one or subtracting the one from the value. Now, where could you use this? Well, if you recall, when we did accounting with loops, you're often incrementing one to go towards the termination condition, and that's exactly what these are, one of the things that these are good for. So this right here, I'll ask you to do this actually as kind of an exercise. You're not turning in anything for it, but I would like you to try to figure out what is the difference between the post-increment version and the pre-increment version. Okay, so I want you to write out the code that's right here on this slide 136, and I want you to see what does the output look like and why is it doing what it's doing. Okay, and then these are the operators and how they fall into the precedence. So the associativity and how everything works as far as their types. So the unaries fall after the postfix. The unary prefix falls here, and then you have multiplicative, additive, etc. So if I wrote a statement like C++ times 12, which one would be performed first? And you'd look here and you'd say, well, the plus plus would be performed first, okay, before the multiplication. So this is precedence. So this is getting a little bit more extensive than please excuse my dear Aunt Sally. So just keep these in mind. Most people don't necessarily memorize these. A lot of people use parentheses to make sure things are clear what they're doing. So even if the precedence is correct, sometimes for clarification purposes, programmers use parentheses, or because they're not sure. So it's totally acceptable in most scenarios. It actually makes the code more readable. So a lot of people put parentheses around statements like C++ times 5. They would put parentheses around the C++ or 5 or A++ or what have you. Even though this unary prefix or postfix have associativity or have precedence over the multiplicative operations, because it would look kind of hokey if you put C++ plus 7. So that could get a little bit confusing. So parentheses are your friend. Alright, so that's pretty much all I have for you. I would say for a summary of all this, I know that's like an overwhelming amount of information. You're not going to memorize it all right away. Some of the stuff I would just say to get familiar with. Make sure you're comfortable with the compound operators, with the increment and decrement operators, and also be familiar with the control structures that we learned today. Be able to categorize. So you should be able to know what sequential control means. What does iterative or repetition control mean? What does selection control mean? What are the differences? How do they work? What does the condition do, the predicate? So if statements, if else, and we also covered while today. So next week we'll cover the switch statement and then the for loop and the do while loop. So this week we did 2 selection control structures and 1 repetition control structure. Next week we'll do 2 repetition control structures and 1 selection control structure. Alright, so if you have any questions, please feel free to email me or post on the discussion board if you're still having problems with Visual Studio. But I do highly recommend, if you're still having problems at this point, just download the Express version. Not from DreamSpark. Don't download from DreamSpark. I put a link on the news feed, so just look into that. Alright, thanks and have a great day.